Hi everyone, and thanks for joining us for our discussion of mountain wave. Right now we're working our way through different types of mountain waves. We already discussed in another video vertically propagating waves. Now we're going to look at trapped Lee waves. A trapped Lee wave is, of course, a mountain wave that develops when all of the energy in the atmosphere is confined to the lowest layers or lowest altitudes. And the reason for this is there's strong shear in the atmosphere. With strong shear, it kind of holds down all of the energy into the lowest layers, does not allow anything to propagate vertically. So what you need for a trapped Lee wave is, of course, a stable atmosphere, typically stable in the lowest layers and maybe slightly unstable aloft, but with kind of a temperature inversion right at mountaintop. Don't worry about those details. These are for meteorologists forecasting. But the one thing that pilots should know is that if you have strong shear in the atmosphere, meaning that as you go up in height, the winds increase dramatically with altitude. That typically causes a trapped Lee wave. Now, these waves are typically the ones that pilots are taught in their ground school classes. These are mountain waves that extend hundreds of miles downwind of a mountain, but they don't go very high, typically only a few thousand feet above the mountaintop, and they stay up to usually mid-altitudes, maybe 10 to 15,000 feet. And of course, there is no vertical tilt with the wave like you saw with a vertically propagating wave. And with the trapped Lee wave, you also usually see lenticular clouds, whether they be mid-altitude, in other words, alto cumulus standing lenticulars, or high altitude, which would be cirrocumulus standing lenticulars. And I think that you probably know how lenticular clouds form. Usually lenticular clouds form as air rises and cools, it reaches the dew point, and you have condensation forming, which produces the cloud. As the air descends, it warms up, it evaporates the water droplets, and the cloud disappears. So the cloud does not move, it kind of stays in one location in the crest of the wave. Now, that's assuming that there is enough moisture in the atmosphere to produce a cloud. So what you see with a trapped Lee wave is a train of lenticular clouds downwind of the mountain. And you'll see several lenticular clouds, maybe hundreds of miles downwind, depending upon the strength of the wind and the stability of the atmosphere. So sometimes these lenticular clouds may be multi-layered. It depends upon the moisture profile upwind of the mountain and upwind of the wave. What happens with these multi-layered clouds is that you'll have layers of moisture and then layers of dry air, so that as the air is forced to rise, you get clouds forming at different layers, and they have quite an impressive structure. Also, another thing about the wave is if you look at the lenticular cloud, that usually tells you about the turbulence associated with the wave. If the lenticular clouds look nice and smooth, then the wave doesn't have much turbulence up high, and you'll get a smooth ride except for the updrafts and downdrafts. And this is an example of what a laminar altocumulo standing lenticular cloud looks like. But usually with trapped Lee waves below those lenticular clouds, you might have more turbulent lenticular clouds. And they give you an indication, of course, that you're going to have turbulence at lower altitudes typically. Now remember that you get clouds if there is moisture. If there's no moisture, then you won't get clouds, but you still can have wave even without the presence of lenticular clouds. Most of the hazards associated with trapped Lee waves are at low altitudes. Typically, of course, we said that you get strong shear that produces this type of wave. And you remember that strong shear usually induces turbulence. And that turbulence usually is at lower altitudes. So below the height of lenticular clouds, perhaps you'll find the turbulence. We call this the lower turbulent zone, and usually that's a few thousand feet above the ridge level and below. So if the mountains are 12,000 or 14,000 feet, like you see in the Colorado Rockies, then you can expect turbulence 15 and below whenever you have a trap-lee wave. So of course the trap-lee wave results from the strong shear, and the strong shear produces strong turbulence at low altitudes. So you'll have strong turbulence, especially in the troughs and the ridges of the wave. And of course, it goes without saying that trap-lee waves, since it is a wave, you will also have strong updrafts and strong downdrafts. So when you're forecasting a trap-lee wave, what do you look for? Of course, the winds need to be perpendicular to the mountains, and the FAA says that a minimum wind component of 20 knots at the mountaintop, is enough for mountain wave activity. Also, another thing that you can look at is the jet stream. If you have a very strong jet stream moving over the mountains, remember jet streams are typically up at about 30,000 feet. It means that you have strong shear with typically weaker winds at lower altitudes. So a strong jet stream moving over the mountains usually is an indication of trap-lee waves. But like we did with the vertically propagating wave, you can do a calculation, and that is the 1.6 rule, where you look at the winds at the ridge level. In this case, we have 60 knots at 12,000 feet, and then go 6,000 feet above that. Here you have 120 knots at 18,000 feet. And take the ratio of those two. So here you're dividing 120 by 60, that gives you 2, and 2 is greater than 1.6, and it'll produce trap-lee waves. Remember, trap-lee waves means you have strong shear, and vertically propagating waves means that you have weak shear. Other things that you can look at for trap-lee waves, of course, look at airmets, sigmets, and other turbulence products. Typically, if it's low altitude, in this case, looking at this sigmet, it says that there's turbulence below 12,000. That means low altitude turbulence over the mountains usually indicates trap-lee waves. So you'll have turbulence down low, but typically a smooth ride aloft. Also, check in pilot reports. If aircraft are reporting turbulence down low but nothing up high, that's another indication of a trap-lee wave. And then, of course, strong winds near the surface usually also is an indication of trap-lee waves. But probably the best way to identify trap-lee waves is by looking at the satellite imagery. And here you can see lenticular clouds over Pennsylvania, New York, New Jersey, Vermont, New Hampshire, Massachusetts. And those lenticular clouds are the dead giveaway for a trap-lee wave. Also, as we said, 20 knots at the ridge top is a good indication of the likelihood of wave activity. So we're done with the different types of waves. We're going to look at other weather phenomena that happens in the mountains in our next video.